So for that, I'm gonna import the optimizer first. For that, torch.appteam, and I'm gonna declare, sorry, I'm gonna assign it to the variable called optimizer, and I'm gonna use the Adam optimizer here, which is the pretty common optimizers being used in almost most of the neural networks. So we are going to use that optimizer. Optimizer will be very useful to change the parameters, adjust the parameters and the weight values in the neural network. So once the forward pass is done, we will get the loss, and then the loss will be calculated based on some mean squared error, and then that loss will be passed back to the network using the backward propagation. And then after the backward propagation, the optimizer will come into the picture and then will optimize all the weights according to the loss values which we found in the backward propagation. So that's why we need the optimizer. For that, we are using the Adam optimizer. And here we are going to pass it to all the parameters of our deep neural network which we have created. So if we say this, then this this Adam optimizer will be applied to all the parameters which we have defined here. So just like as I said, like in the activation function, so if you say to one layer, it will be applied to all the neurons in that layer. So if you say to this if you just say the deepnet.parameters, which means it will this Adam function will be optimizer functions will be applied to all the neurons of the neurons of our neural network. You can also mention that that this optimizer could be applied to only part of our neural network, but that is on the later stage. But since we are building the neural network from the scratch, we have to apply the optimizer to all the neurons. So we're going to apply to all of our deepnet parameters. And then here you have to mention the learning rate. Here I'm going to say 001. So this is the size of learning rate which would be mentioned to learn. Based on this learning rate only, the weight and weight and biases are optimized in the neural network. So if you keep the learning rate low, then it will make your neural network to learn quickly, but it will lose a lot of features. Learning a lot of features. But if you keep the learning rate very low, then it will learn. The learning rate might be low, but learning time may take long, but it will learn a lot of features. So usually people use the adaptive learning rate that we are going to see in the advanced level. But now just keeping the low learning rate, 001 is very moderate. So if you keep this learning rate would be sufficient to optimize and to learn the features, because we are going to use the simple number identification from an image. So this learning rate is very sufficient. And we are gonna declare the epochs, the number of epochs that we are gonna pass the data set. So we have only one data set, but one data set contain multiple images and labels, but we have only one data set, which is MNIST data set. So we have to pass that one data set into multiple iteration into our neural network. So that one data set, one iteration is called epochs. So we will pass the same data sets into multiple times into our neural network. That will create more more dynamics and randomization in our neural network learning. I mean training. So we're gonna pass 3 times our data set to the neural network. So that is why we are going to declare epoch. That iteration is called epochs here. So we're going to declare that epoch is 3. So we're going to pass it 3 times. So here we are going into the loop and pass the neural network. Range of epochs. And we are going to take the data one by one. We're going to pass it to our neural network. So I'm going to take the data from the train set, and so I'm going to separate the input and output. Input is our image, batch of images, and output which means labels or label batch. So here I can also print and show you what it contains. Label batch. So it contains 3 because it's running 3 times since we declared the epoch as 3. So each time it's picking up one data, and it shows the since we declared that a batch number is 10, it contains the 3 numbers in the label tensor. So this is the output batch. This is from first epoch. It contains 10 numbers. First number is 2, 0, 2, 2. So we can also print the we can also display the image as well. So let's go and write how to feed the this data into the neural network. So let's write the important steps of feeding the data into our neural network. So for that, I'm going to use the DeepNet, our neural network instance. Then I'm gonna call the zero-grad function every time before feeding the batch of data into our neural network, because this has to be the gradient should be initialized back to 0 whenever we feed the batch of data into our neural network. Otherwise, when each batch finishes, the neural network gradient value get increased, and then it will get added up on each and every batch iteration. So that will create some error in the output. So for that we need to call this function, which will initialize the gradient back to the 0. So the next one is we are going to pass the input data which we taken from the data sets. For that, whatever we have done here, that we are going to do it here. So here we have done with the random tensor, but here we are going to do with our data from the data set. So instead of X, I'm going to pass the image batch here. So instead of calculating 28 by 28, I mean multiplying every time, I'm going to pass the multiplied output 784. So now we got the output. Now we have to calculate the loss. So calculating the loss, we have to use the functional module dot NLL loss. This will compare the desired output and the actual output, and then calculate the loss by mean squared error. So for that we need to pass the output here. So this will give the actual output, and then the desired output is our label. So we pass these two things. So this will calculate the loss, and then it will be stored in the, this will be the loss will be available for this iteration in our loss variable. So we need to pass this loss backward into the back to the layer at the back. For this we need to just call the backboard loss.backboard. So this will automatically pass the loss to the backward layers until it reaches the input layer. Then once the loss has been passed towards all the layers, then we have to do the optimization function to adjust the weights based on the loss. So for that we need to call our optimizer. Since we have already applied this function to all the neurons, we just need to calculate once the loss has been defined in all the layers. So that's it, it's done. So we are going to print the our loss on each of our epoch. So let's see. This is going to train our neural network. I'm going to run this. It may take some time since I'm using the CPU version of Pytorch. It will be much more quicker if you're using the GPU version. Before we get the output, we just before it get trained, we can do some accuracy check. We can do some code. We can add some code for accuracy check. For that, I'm going to declare a few variables. So you can see the first epoch is finished. I'm getting the loss value as 0.0119. In the next epoch output, I should get below than this, or maybe nearer to this value. Let's see. Let's wait for the third epoch to finish. So here we are going to do some, you can see the second one. It's almost, it's not very it's a huge difference between these two values. Let's see the final one. It should be below than the first one, the final value. Anyway, nothing to worry. I guess the loss is very minimal. It's not 0.9 or 1.0. So it's just 0.0 and 0.1, which is acceptable. So we are going to calculate the accuracy of our neural network. So it is 0.06 the loss. So it's almost 0. So let's check the accuracy of this neural network. With the torch dot no grad, we are not applying any gradient here. So we are taking the data from our training set. and we're gonna iterate it. Image label is equal to data. So here output is gonna be same as this one. And I'm going to get the index of this. I'm going to get the output values from the data sets, and I'm going to compare the output value of our neural network. So if it matches, then the correct is going to be increased. Excuse me. If it doesn't, then the correct is not going to get increased. So I'm going to enumerate the data set. Enumerating the data sets or output or same. I mean, like dataset output, I mean like dataset label or output is gonna be same, since both is gonna be 10. Torch dot argmax. Argmax, which is nothing but like if it is 0.9, then it'll be I'll tell you. Why label if it matches with the output, the dataset, the output value matches with the dataset value, then the correct is gonna be increased. We are also going to calculate how many number of data that we have checked here. So here the argmax, which will show that if you pass an array which contains 0.4 comma 0 sorry 0.1 comma 0.7 then it will pass the value as 0,0,1. So that's the way, I mean, like the maximum value of the array will be calculated. Then that will be rounded up as 1 and will be passed here. And then the accuracy can be calculated by dividing the total, so dividing the correct value by total. Sorry, we should put comma here. It will take some time. Our network got trained now. Now we're going to see the accuracy of this accuracy of our deep neural network. So it is 0.97, which is good, but like getting above 0.8 or 0.85 is a good thing. Don't try to train your model to reach 1.0, which will actually gives you the which will actually make your model to overfit Overfitting means which your model is very good at predicting your data set which you actually fed, but it doesn't predict the data which you gives other than your data set. So usually just keep it more dynamic, train it up to 0.85 to 0.95, which is a good value. I mean, the accuracy should be between these values, then it is a good predicting model. If it is more than that, or if it is below than that, it will be less accurate. So let's go and check the output. So our model is gonna predict well, since it's gonna show the accuracy value is 0.97, which is very good. It should predict all the data from this data set. So for that, I'm gonna import the pyplot from matplotlib. As penalty and dot imshow to show the image that I'm gonna say image dot 0 dot view 28 by 28. So if I click run, so it's showing the output as 6. So I'm gonna show the output of, sorry, I'm gonna print the output as well. Label of 0. So if I run it, you can see the 6 and 6, 1 and 1. So I'm picking the different image and label. So it's 1 1 9 9. The number is 9 and the image is 9. So you can just keep on checking this with the different image and value. So it's, oh sorry, let me keep 4 4. So there you go, we have printed the image and the output from the data sets, but now we're going to print the output from our deep neural network then check whether it matches with the actual data set output. So for that, we're going to print the torch.argmax. Then we're going to pass the same image, but here we have to flatten it since our neural network expect it in flattened way, which is 784, as like we passed here, and then close it and then get the 0th element. Oops, I think that's the problem here. Sorry, 0th element of that data. What? 154? Sorry, we are not passing, actually we are not passing into our deep neural network. Whatever. So I'm just simplifying it, like I'm getting the output from our deep neural network and then calculating augment max from the output and then passing the 0th index of the argument max output. So there you go. So here is our deep neural network output, and then calculating the argument max from the output. We are getting the same value as the data set value. Here is the data set value, data set actual desired output, and this is our actual output from the neural network, and this is the image. Let's check with the different index. 6. There you go. Our network is predicting very well. So I can also comment it. So that you could get the better understanding. So that's it. It's predicting really good. Again, it's 4. Okay, that's it, guys. So this is about how to use the MNIST pre-built data sets, and how to train the neural network using those data sets. So building the neural network and training is very easy if you're using the Pytorch neural network module. It's very simple, and even the data sets which we access is also very simple data sets. It's 28 by 28 image data set, which is very simple and which is very clean and neat. If you're gonna build our own data sets, definitely it's hard, because collecting the data sets and cleaning up and labeling them is really hard task than building the neural network and training them. So we are gonna do a lot of learning about building our own data sets and building the complicated convolutional neural networks on our coming up tutorials. So this is the basic learning about the Pytorch. You can just feel free to play around with the other pre-built data sets with your own neural network. So good luck, guys. Thank you so much. Cheers.